Give me your number, I call you up. You act like you're gonna interrupt. I don't have no trouble with you fucking me, but I have a little problem with you not fucking me. Baby, you know.
Hi, I'm John. I'm a chemistry graduate student at UCLA. And now in this video, we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course. Now we're going to go over interpretation of NMR spectra. And so examples of really trying to determine structural information in problems is in a separate video combined with IR, spectroscopy, and mass spec. And so these are just really looking at those correlation tables to see what chemical shifts you would expect to find different protons attached to different functional groups. So to start out with alkanes, they're kind of boring. All hydrogens and alkanes are very similar in chemical environments. And therefore, the proton NMR chemical shifts of alkane hydrogens fall within a very narrow range of about 0.8 to 1.7. So you'll see in another video that the chemical shifts of alkane carbons in carbon-13 NMR fall within a considerably wider range of a chemical shift about 10 to 60. The chemical shifts of vinylic hydrogens are larger than those of alkane hydrogens and typically fall in the range of 4.6 to 5.7 ppm. The vinylic hydrogens are deshielded by the sp2 hybridized carbons of the double bond and the local magnetic field induced by the pi bond of alkenes. The splitting pattern observed as also dictated by the coupling constant can also give you some additional information regarding the double bond about whether the molecular structure has a cis or a trans conformation. So the coupling constants are generally larger for trans vinylic hydrogens than for cis vinylic hydrogens. And so what that means is that in the signal splitting pattern, a larger coupling constant is going to give a greater separation distance between the peaks. The chemical shift of a hydroxyl hydrogen in a proton NMR spectrum is variable and depends on the purity of the sample, the solvent, concentration, temperature, a variety of things. It often appears in the range of 3 to 4 ppm, but depending on experimental conditions, it may appear as far upfield as 0.5 ppm. The hydrogens on the carbon that bears the hydroxyl group are deshielded by the electron withdrawing inductive effect of the oxygen atom, and their absorptions also typically appear in the range of 3.4 to 4. So again, these values you can find in your textbook as well. Now for ethers, the most distinctive feature is the chemical shift for the hydrogens that are on the carbons bonded to the ether oxygen. The signals for this type of hydrogen typically fall in the range of 3.3 to 4 ppm. And this corresponds to a downfield shift of about 2.4 units compared to their normal position in alkanes. And so this is pretty dramatic and can be pretty indicative if you have an ether. For aldehydes and ketones, the signal for an aldehyde hydrogen typically appears between 9.5 and 10.1 in the spectrum. Because almost nothing else absorbs in this region, it's very useful for identification. The hydrogens on an alpha carbon or the carbon directly adjacent to a carbonyl of an aldehyde or a ketone appears around 2.2 to 2.6. Carboxylic acids and esters. Signals for hydrogens on the alpha carbon to a carboxyl group in both of these functional groups appear in the range of 2 to 2.6. The hydrogen of a carboxyl group gives a very distinctive signal in the range of 10 to 13 ppm. So this is downfield of most other types of hydrogens, even farther downfield than that of an aldehyde hydrogen. And this is easy to serve to distinguish carboxyl hydrogens from most other types of hydrogens when you're trying to elucidate the structure. And then finally for amines. The chemical shifts of amine hydrogens, like those of hydroxyl hydrogens, vary quite a bit between 0.5 and 5 ppm, depending on the experimental conditions. As in alcohols, the exchange is very fast, and so spin-spin coupling or spin-spin splitting between amine hydrogens and hydrogens on adjacent alpha carbons is averaged, and so generally the amine hydrogens appear as very broad singlets.